Our next topic includes a discussion about bonding. We're going to be looking at how all of the atoms that we predict from Lewis structures will make the bonds that we predict based on those Lewis structures. So the theory of bonding that we're going to be looking at is called VSEPR, and it stands for Valence Shell Electron Pair Repulsion Theory. And at the heart of this theory is the idea that electron groups are going to repel one another. So that if we have to place a certain number of electron groups around a central atom, we're going to keep those groups as far apart as possible. We're going to be looking at the details of how central atoms accommodate a specific number of electron groups between 2 and 6 electron groups, and exactly all of the ways that they will be able to accommodate that electron density and those groups. The first thing that we need to be able to do is we need to be able to count our electron groups. So that if we look at the identity of an electron group is anywhere around a central atom that we have electrons. A lone pair counts as one electron group. A single bond counts as one electron group. A double bond counts as one electron group. A triple bond counts as one electron group. And if you had an unpaired electron, that would also count as one electron group. So a lone pair represents 2 electrons that belong just to the atom to which they are bound. A single bond represents 2 shared electrons. A double bond is 4 shared electrons. A triple bond is 6 shared electrons, and an unpaired electron is 1 electron. And so these are the types of electron groups that we have, and each of these is going to count as 1 electron group at a central atom. So each counts as 1 electron group at your central atom. And that's really important, because when we talk about the shapes of molecules, it's going to be based on our initial identification of the number of electron groups that are present. So that if we look at a couple of examples, I want you to pause the video and look at each of the 5 molecules you see here. Focus on the central atom and count the number of electron groups. When we look at the structure of water, in number 1, oxygen is our central atom. The oxygen in this structure sees a total of 4 electron groups, and the identity of the electron groups are that this oxygen sees 2 lone pair for our first 2 groups, and 2 single bonds that give us a total of 4. In number 2, if we look at the structure of formaldehyde, we have 3 electron groups. And when we look at the identity of those groups at the carbon, which is our central atom, the carbon sees a double bond to the oxygen. That counts as 1 electron group. The carbon also sees 2 single bonds to hydrogens to give me electron group number 2 and number 3 for a total of 3 electron groups. In the case of H-CEN, I have 2 electron groups. The carbon sees a single bond to the hydrogen and a triple bond to the nitrogen. Each of those represents a place where the carbon must see electron density for a total of 2 electron groups. Remember that it doesn't matter whether the carbon is sharing 2 electrons or 6 electrons with its neighboring atom. In this case, the carbon sees electron density at 2 positions, and so that will be the number of electron groups. In number 4, the sulfur is my central atom, and the sulfur in this case sees 6 electron groups. And in number 5, the nitrogen is my central atom, and it sees a total of 4 electron groups. So as we begin to look at the 3-dimensional shapes of molecules, there's going to be videos assigned that will go through the details, but let me give you a little bit of a preview. If we have a central atom that sees 2 electron groups, in 3-dimensional space, that central atom, which is this position right here, is going to try to keep these 2 electron groups as far apart as possible from one another. That's going to minimize the electron repulsions and maximizing the space between those groups. So that if I have two groups in three-dimensional space, I will be able to keep those two groups farther apart than any other number of electron groups that I have. When I have two electron groups around a central atom, I'm able to keep those groups as far apart as possible with a bond angle of 180 degrees and an electron group geometry of linear. So my first group is here, my central atom is here, my second group is here. If I have a central atom that has 3 electron groups around it, my 3 electron groups are going to have to be closer together in three-dimensional space than what I can do for 2 electron groups around a central atom. I'll have to put more things around that spherical central atom, so my groups are going to have to be closer together. I'm able to do that with a trigonal planar electron group geometry and bond angles of 120 degrees. Once I get to 4 groups around a central atom, this will now be where my electron groups occupy a three-dimensional shape, so that if you look at this three-dimensional shape, you see that I have a central atom, which is right here, and I have 4 electron groups around that central atom. So 1, 2, 3, and 4. And these 4 electron groups in three-dimensional space are going to give rise to an electron group geometry that I call tetrahedral, and the bond angles between my groups, so from here to my central atom to here, are going to be 109.5 degrees. If I have to put 5 electron groups around a central atom, I also have a structure that has a three-dimensional shape to it. And as you look at this three-dimensional shape, what you notice is that this is essentially a combination of 2 shapes that I've already seen. It's going to be a combination of my trigonal planar shape and my linear shape. And as I put these shapes together, what I see is that I have 5 groups around my central atom, and the 5 groups around the central atom are going to give rise to an electron group geometry that I will call trigonal bipyramid. And in this trigonal bipyramid structure, I have 2 different positions. I have these groups here that occupy the top and the bottom of the molecule, if you will, that come from that linear component. These groups are called my axial positions in the structure. These groups here that go around the middle that come from that trigonal planar component, these groups are called my equatorial positions. And in a structure, something that's going to go in an axial position is always going to be closer to its neighbors in three-dimensional space because it will see all of these equatorial groups with bond angles of 90 degrees. Something that sits in the equatorial position right here is still going to see some of its neighbors with bond angles of 90 degrees, but these groups here will also see other neighbors with bond angles of 120 degrees coming from that trigonal planar component. So a group that is bigger is going to be sitting in these equatorial positions because those groups will simply have more space, and it's yet another way for us to minimize the repulsion of the electrons between all of the groups we place around a central atom. Our final shape we'll deal with occurs when we have 6 groups around a central atom. And as you look at having 6 groups around a central atom, you see that I have 1 group here and 1 group here, and then I have 4 groups that go around the middle as I look at this particular structure. This is what we call an octahedral electron group geometry, where I have 6 groups around my central atom. They're distributed symmetrically throughout this shape, and I have bond angles of 90 degrees between any 2 electron groups in my central atom. I have bond angles of 90 degrees throughout this structure. So with this octahedral electron group geometry, this is how I will keep 6 groups around a central atom as far apart as possible, minimizing the repulsions between all of the electrons that are shared in this case.